We're talking about approximation algorithms. So let me review the motivation and some classification of approximation algorithms. The motivation is that many important decision problems may not admit a solution in polynomial time. Often one cannot prove that they do not admit a polynomial time solution, but you all know the P versus NP problem. So when it has been shown that a certain decision problem is NP complete, then don't waste your effort in finding a polynomial time algorithm for it. And with many important decision problems, I refer to this catalog of, I think it's about 400 problems that have been proven NP complete. So for these, we cannot expect a polynomial time solution. But many of these hard problems arise from optimization problems. And the nice thing about optimization problems is that we can talk about approximating an approximation problem. We cannot really talk about approximating a decision problem. What is an approximate yes or an approximate no? People have, including myself, have tried to define that and investigate, but for the sake of this chapter, we're only going to try to approximate optimization problems. Without approximation, one can still do interesting research on such problems. For example, one can look for exact algorithms, which then, of course, need to be super polynomial or even exponential time algorithm. But even among these algorithms, there's some more and some less efficient ones. For example, if we have an exponential time algorithm with running time b to the n, then if b is 100 to the n, that's a considerable difference to an algorithm which has running time 1.01 to the n. 1.01 to the n is also exponential, but obviously it's much more practical than 100 to the n. So, important direction of research among exponential time algorithms, try to find the smallest possible base to the exponent n. Then there's parametrized algorithms or strongly polynomial time algorithms. And actually we're going to return to that when we discuss the approximation for the knapsack problem. But for now, let's return to the question about approximation. And here, our quality measure of an algorithm is the approximation factor or approximation ratio. Like when we discussed online algorithms, there it was the competitive ratio. Comparing to an omniscient offline algorithm. Here, we compare the output of our approximation algorithm to the output of an exponential time exact algorithm. And there are two types of approximation problems, optimization problems, minimization problems, and maximization problems. For minimization problems, the approximation factor is usually, and in this chapter, denoted as the ratio between the approximate and the optimal minimum. So remember, for minimization problem, we want to find a least cost, for example, and C star denotes the optimal, that is the least cost. C denotes the cost that our approximation algorithm returns. And the ratio C divided by C star is therefore greater than 1, right? Greater than 1 for minimization problems. For maximization problems, the convention is the opposite. For maximization problems, the optimum is large. And we want to approximate it from below. We cannot go beyond that, right? So we can only try to get from below as close as possible. And therefore, the numerator and denominators are swapped here in the definition of the approximation ratio, so that again the ratio is larger than 1. We usually use star, superscript star, to denote the optimal answer, and without superscript, the answer returned by our algorithm. And we started talking about the traveling salesperson problem. And the original motivation is indeed trying to visit all major cities of the United States by a tour of shortest length. And this is formalized as a decision problem. Well, originally it's an optimization problem. It's a minimization problem, right? Shortest tour, minimization. And turn that into a decision problem by input of a weighted graph, where the nodes of the graph are the cities, major cities. The weight function assigns some weight to the edges between these nodes, between these cities, the distances. And then there's this additional parameter k, which asks, does the graph, weighted graph, admit a tour, that is, cycle, start in any vertex and visit all the cities and return to the starting city, cycle of length at most k. So the relation to the minimization problem is, if we can solve the minimization problem, then of course we can calculate the optimal k, the least possible k, and that allows us to also to answer the decision problem by comparing the least possible k, k star, to the input k, right? Conversely, if we can solve the decision problem, then we can do some binary search for the optimal k. So we first ask whether there's a tour of some large length using the decision variant. If it is, then we try half that value k. And if there's still a tour of that smaller length k, then we divide it again by half. So that's 1/4. Otherwise, we try 3/4. So using repeatedly solving the decision problem in a binary search, we can get as close as we want to the optimization problem, to the minimization problem. So both have basically the same but unknown complexity because it's NP complete. You might also know the unweighted variant of the traveling salesperson problem, which is simply the Hamiltonian cycle problem. So the differences in the traveling salesperson problem, there's an edge between any two nodes. It's a complete graph. You can travel from any city to any city, although it might cost a lot. So the weight, the cost could be very large. In the Hamiltonian cycle problem, it's not a complete graph. We want to know whether it's possible to start somewhere and visit all vertices without any cost associated to the edges, but we can only use edges that are in the graph. So again, that's a decision problem, but without this parameter, the k, and also without the weight function. Now, intuitively, traveling salesperson problem is at least as hard as Hamiltonian cycling problem. Why is that? Well, we can encode the Hamiltonian cycle problem as instance of the traveling salesperson problem. And we take the input graph of the Hamiltonian cycle, and whenever there's an edge missing, we add an edge, but we give it very, very large weight. Think of it as weight infinite, although in practice it can be just some very large number. And then we ask whether this complete graph, but with these weights, has a traveling salesperson problem as a tour of small weight, so small that it is prohibitive to use any of the additional large weight edges that we have added. And then the answer will be the same for this artificially graded weighted traveling salesperson problem has such a tour of small weight if and only if the original Hamiltonian cycle problem had a tour at all. And then we started talking about the metric variant of the traveling salesperson problem. The metric variant is where the weight function, the distance between edges, between vertices, is supposed to satisfy the triangle inequality. So this is the original traveling salesperson problem with a weight function, which is now promised to satisfy the triangle inequality. So checking whether it satisfies the triangle inequality indeed, that can be done in cubic time, right? We just plug in all triples of vertices A, B, C, and look up the weights and see whether it satisfies this triangle inequality. And intuitively, the meaning of the triangle inequality is that making a detour should not be shorter than going directly. So this is a metric variant of the traveling salesperson problem. And we'll return to the non-metric variant at the end of this last chapter, approximation algorithm. And we discussed the first algorithm, which is maybe better called the double tree algorithm, which uses the fact that we know how to calculate a minimal spanning tree in polynomial time. So we do that. And then we traverse that minimal spanning tree in order, depth first. So remember what is an in-order traversal of a tree. So there's pre-order, in-order, and post-order. In-order means first the left tree, then the node, then the root, then the right subtree as a recursive algorithm. Pre-order means first the root, then left subtree, then right subtree. So pre means the root first. And post-order means first left subtree, then right subtree, then the root. The important thing is depth first. So we go down all the way first before returning to the root or proceeding to the next subtree. We've considered an example, some input, some vertices on a grid, and implicitly we suppose that the edge weights, the distances are given by the Euclidean distance between these vertices on a grid. And the first step of the double tree algorithm would calculate the minimal spanning tree. Let's say this is a minimal spanning tree. And the next step is to traverse this minimal spanning tree in order, depth first. And then we saw why it's called the double tree algorithm, because what does it mean to traverse in order, depth first? So we start at the root A, And we first go to the left subtree. The left subtree is that with root B. So from A, we go down the edge to B, and then comes the recursion step. Now we recursively traverse the subtree at root B, which means now we traverse the edge from B to C. Then there's nothing to recurse further into. So we return to B. That's the in order step. And then we proceed to the right subtree of B, which means now we traverse the edge from B to H and then back. Now you already see that we traverse each edge twice, right? So we went from A to B, then from B to C, and then from C back to B. So the edge between B, it's undirected, is traversed twice. That's why it's called the double tree algorithm. Then from B to H, and then from H back to B, and then from B back to A. So also the edge between A and B is traversed twice. And then proceed to the right subtree of A from A to D, from D to E, from E to F, from F back to E, edge traversed the second time, from E to G, from G to E, back, from E to D, back, and from D to A, back. So that's the traversal in order, depth first. And the order in which the nodes are visited here are A, B, C, H, D, E, F, G, A. And observe that here we've made shortcuts. We've avoided visiting the node twice. So the original traversal says A, B, C, B, H. But we skip the second visit to B. Instead, we go directly from C to H. And that's where the triangle inequality, the hypothesis of a metric TSP, comes into account. Going from C directly to H by this promise can be no longer than going from C to B and from B to H. So that this traversal results in the following traveling sales tour. And then we compared that to an optimal traveling sales tour, which would be given by A, B, C, H, F, G, E, D, A. And remember, we use the superscript star to denote the length or any other parameter for the optimal answer to our optimization problem. So that was an example run of the double tree algorithm. And then we started to prove that the double tree algorithm, move that here, the double tree algorithm has approximation ratio 2. Remember what that means? We're talking about a minimization problem. So the approximation ratio is the tour which we return, the length, compared to the unknown optimal tour. And approximation ratio 2 means our double tree algorithm will return some tour which is promised to be no more than twice as long as the unknown optimal tour. So, and here's again the review of the proof. For the proof, we consider the sequence F of edges traversed by our in-order traversal, C, the tour that our algorithm outputs, and C star, the unknown optimal tour. And we denote capital L, the length of any sequence of edges or any set of edges added up. And the first observation is that, remember, the first phase of the double tree algorithm was to calculate a minimum spanning tree. Now, if we take the unknown optimal tour C star and remove any edge, then this will be a spanning tree. What is a spanning tree? It connects all nodes. Well, yes, the unknown tour connects all nodes, and it contains no cycle. Well, the unknown tour contains or is a cycle, but we've just removed any edge from this unknown tour. And since the edge weights are non-negative, removing one edge not only breaks the cycle, resulting in a spanning tree, but also will not increase the total length. That's why the hypothesis is so important, that our edge weights are non-negative. Otherwise, removing an edge could actually decrease the length. So that means we have this inequality Roman 1, the total weight of the edges of the minimum spanning tree. It's by definition a minimum spanning tree, can be no larger than the total weight of the edges of the unknown optimal tour, even after removing any edge in this unknown optimal tour. First inequality. Then we use that this is a double tree algorithm. Double tree meaning that every edge is traversed precisely twice. Double tree algorithm. So any edge in the minimum spanning tree appears precisely twice in the traversal. That's how we created the traversal, right? Going down and up again, which means that the total weight of the edges in the traversal is precisely twice the total weight of the edges in the minimum spanning tree. Second inequality. And third and last inequality, the total cost of the tour that our algorithm finally outputs is no more than the total cost of the traversal. And this is again where the triangle inequality hypothesis is crucial, because remember how we create this final output tour. We take shortcuts. Instead of going from C via B to H, we go directly from C to H, omitting some of the edges in F and skipping some. And by hypothesis, this cannot increase the length taking these shortcuts because of triangle inequality. And then putting these three inequalities together, we see that the length of the tour, the circle output, is at most the length of F, the double traversal, which is twice the length of the minimum spanning tree, which is at most twice the length of the unknown optimal tour, and therefore the length of the tour output by our double tree algorithm can be no worse than twice as bad as the length of the unknown optimal tour. So this is again an example of, relative performance measure. Not any guarantee about the absolute length, which can be very large, but about how much worse our approximation algorithm length outputs compared to the unknown optimal, very similar to the competitive analysis. And now, let's improve that. Let's proceed from the double tree algorithm to the Christofides algorithm, which yields an approximation factor of 1.5 instead of 2. So in this sense, Christofides algorithm is better than the double tree algorithm. Comparing the performance of algorithms not empirically, not heuristically, but in a rigorous sense using algorithm analysis. So this is going to be on Christofides algorithm. Yeah, Nico Christofides, and he came up with this algorithm where he was actually doing research, economics research. He was really trying to minimize tours in UK. So what's the difference between Christofides algorithm and the double tree algorithm? Where does this improvement come from? So the first step is the same. Compute a minimum spanning tree of the input graph. The idea is, instead of traversing that minimum spanning tree with each edge twice, instead calculate a Eulerian cycle. Remember what is a Eulerian cycle? A Eulerian cycle is one that visits every edge precisely once. Hamiltonian cycle visits every node precisely once, in particular every edge once. Eulerian cycle visits every edge precisely once, possibly revisiting some nodes. Now, deciding whether a given graph has a Hamiltonian cycle, remember that's an NP-complete problem. But this small change, Eulerian cycle instead of Hamiltonian cycle, makes the problem computationally easy. There's a simple way of checking whether a graph admits a Eulerian cycle or not. And the test simply says, check whether every node has an even degree. Whether the number of edges adjacent to every node is an even number. If and only if. Well, the graph must also be connected, obviously, but that's also easy to check. Furthermore, once we have checked that a graph has a Eulerian cycle, it's easy to calculate one. Just greedily follow in this way. So, whether a graph has a Eulerian cycle depends on that every vertex has even degree. Once we've found a Eulerian cycle, then we do same thing as with the double tree algorithm. We introduce shortcuts. Whenever the Eulerian cycle circuit visits a vertex again, skip that vertex. Remember, we're talking about a complete graph here, right? And by triangle inequality, introducing these shortcuts will only decrease the length of the cycle output. But in order to calculate a Eulerian cycle, we first must make sure that the underlying graph satisfies this property. Every vertex must have even degree. And for a minimal spanning tree, that's not the case. Right? For example, every leaf has degree 1, right? It has only one edge to its parent, and 1 is not an even number. So we cannot expect the minimal spanning tree calculated in step 1 to admit a Eulerian cycle. And that's where there is room for 3 intermediate steps, 2, 3, 4. And the idea is to add some edges to the spanning tree from item 1 to make sure that then after adding edges, every vertex has an even degree. So to this end, let's identify those vertices in the minimum spanning tree which have an odd degree, and then calculate a minimum weight perfect matching of these vertices So again, that raises the question, two questions. Does there always exist a perfect matching? And then, if it does, then how can we calculate a minimum weight perfect matching? So the good news is there always exists a perfect matching. Remember, we have a complete graph. Now, which complete graphs admit a perfect matching? If the number of vertices is odd, then it cannot have a perfect matching, right? Any graph. But if the number of vertices is even, and the graph is a complete graph, then it has a perfect matching. So in order for step 3 to work, we need to check that the number of vertices, which is O, is even. And this is where the so-called handshake lemma from graph theory comes in. Anyone knows the handshake lemma? Handshake lemma basically says the number of vertices of odd degree is even. It's almost a haiku, right? The number of vertices of odd degree is even. Simple exercise in double counting, but very powerful, and we use that here. Because our set O consists of vertices of odd degree, so it has an even number of vertices, so there exists a perfect matching. First problem solved for step 3. Next problem, how can we find even a minimum weight perfect matching with respect to the given weights? And this is actually a little bit less obvious. One algorithm, famous algorithm, is, for example, the Blossom algorithm of Jack Edmonds from 1965. But nowadays there are other algorithms, for example, using linear optimization. Remember, we talked about simplex algorithm. So long story short, yes, step number 3 of the Christofides algorithm works. And what is step 4? Step 4 forms this multigraph. Take the edges of the minimum spanning tree, which, remember, still contains some vertices of odd degree, and then add the edges of the perfect matching, which also makes sure that all the other vertices, which previously had an odd degree, now based on the perfect matching, right? That's another thing about perfect matching. Adding an edge to each of these makes the degree even. And then we're in business. So that's the Christofides algorithm. And then, step 5, calculate a Eulerian cycle in this enhanced minimum spanning tree with the edges added from the perfect matching to make kind of correct also the vertices which previously had odd degree now have an even degree. Let's look at the illustration of this algorithm, shall we? So let's say this is a minimum spanning tree calculated in step 1. What is step 2? Identify the vertices of odd degree in this tree. These are the vertices of odd degree. All leaves, but also in this example, some inner node and even the root has odd degree, right? And then calculate some perfect matching among those vertices. Here you see some perfect matching among those vertices. And that minimum matching exists because the number of vertices of odd degree is even, right? So in this example, there are 8 vertices of odd degree, and 8 is an even number. And therefore, there exists a perfect matching in the complete graph, not in the minimum spanning tree, but we always have this complete graph with possibly large edge weights between, but there is an edge between any of these. So that's step number 3. And then form the multi-graph, which you already see here. That's step number 4. And then calculate some Eulerian circuit, and then again do the shortcutting to turn it into a Hamiltonian circle that visits every node precisely once. So that's an illustration. I've already asked the rhetorical question and answered, why does a perfect matching exist? It's because of the handshake lemma. Let's now proceed to the analysis. Why does Christofides' algorithm guarantee this better approximation ratio of 1.5 instead of 2? To this end, again, we consider the unknown optimal tour. Let's say this C star is the unknown optimal tour. Okay? Yeah, there's some mismatch, to be honest. The number of vertices is different, but this is for conceptual visualization only. This is for analysis, right? We've already stopped discussing the algorithm and now we analyze the algorithm. And the first observation is the same as for the double tree algorithm. The weight of the minimum spanning tree calculated in step 1 is at most the weight of the unknown optimal tour for the same reason as before. Now let's mark in the unknown tour the vertices of odd degree from the minimum spanning tree calculated in step 1. Let's say these are the vertices which in the minimum spanning tree, okay, so the unknown optimal tour is not something our algorithm deals with, but our analysis does. Our algorithm identifies vertices of odd degree in the minimum spanning tree, and for the sake of analysis, we now mark these vertices in the unknown optimal tour. And continuing for the sake of analysis, we now connect these vertices. First, every second of these vertices to every third. Well, no, let's say every odd vertex, odd numbered vertex. You get the picture, right? So we take first odd vertex, marked vertex, and connect it to the next. Then we skip. Then we take the third marked vertex and connect it to the next. And then we skip and look at the next marked vertex and connect it to the next. And we mark these connections, these edges with green. And remember, always we're talking about complete graphs, so these edges exist. And by triangle inequality, the length of these edges can be no more than going the original way in the original unknown shortest tour. Following this curve can be no shorter than going directly. And same here and same here. And then we draw another class of edges, this time in red, that connect the skips that we just made. So no, first let's draw these edges in the minimum spanning tree. And observe that these edges give rise to a perfect matching among the marked odd degree vertices, right? So that's how we created this in the unknown optimal tour, right? Transferring these edges back to the minimum spanning tree creates perfect matching among the vertices of odd degree. With this added, with this multigraph, step 4, now every vertex has even degree. Yeah, double check that. Now every vertex has even degree. That's why we did this. But now we're going to do the same thing again, this time with red edges. And the red edges also connect in the unknown optimal tour marked vertices within the original minimum spanning tree had odd degree, but now every other vertex again. Yeah, you get the idea. So same here, and then transferring these red edges into the minimum spanning tree gives another perfect matching, right? Now we have two perfect matchings among the vertices of odd degree. In step 3, we have calculated a minimum weight perfect matching. So the minimum weight perfect matching M, by definition, has weight less or equal than the weight of green M star, which is just any perfect matching. And M also has weight less or equal than red M star. Right? That's the definition of minimum weight perfect matching. What can we say about the weight of the green minimum matching, perfect matching, and the red perfect matching? Well, these matchings together form a subcycle of C star, right? Together. So if we add them, the weights of the green matching and of the red matching M star, because we're doing shortcuts in the unknown cycle, their weight together will be less or equal than the unknown weight of the unknown optimal solution. And then, yeah, this is again using triangle inequality. Yeah, remember the weight of the length of the unknown total solution is just all edges added, but here we have skipped some vertices, introduced some shortcuts, and therefore it's less or equal. Now we use pigeonhole principle. One of the two, green M star and red M star, will have weight less or equal than half the weight of the unknown optimal tour, the smaller of them. That's our second observation. Second observation says the length of the perfect matching we calculate in step 3. It's a minimum weight, and therefore its weight is less or equal than the weight of the particular, not necessarily minimum weight, perfect matching green star, and same for red star. And that weight will be at most half the weight of the unknown optimal tour. Yeah, proof by contradiction. If the minimum is larger than half, then adding them up would exceed the weight of the unknown optimal tour. So that's our second observation. The third and final observation is, how about the length of the circuit we finally output? Well, first let's look at the length of the Eulerian cycle in this enhanced graph. Since we make shortcuts, the length of the cycle we output can be at most the length of the Eulerian cycle. And the Eulerian cycle lives in the edges of the minimum threading tree, enhanced with the edges of the perfect minimum matching. So we have this third inequality. And then we're done. Now again, we can just put together all these inequalities. So the length of the circle we output is at most the length of the minimum spanning tree, which is at most the length of the unknown optimal tour, plus the length of the minimum perfect matching, which is at most half the length of the unknown optimal tour. So their sum is at most 1.5 times the length of the unknown optimal tour. Remember, the pedagogical concept behind this lecture is beyond knowledge. So if you suppose I would ask you in the final exam to describe Christofides algorithm, then you would maybe write down these 6 steps. I should forward this. Yeah, the pedagogical goal behind this lecture is to raise you beyond knowledge. Knowledge would be a question, maybe in the final exam, to describe Christofides algorithm. And then you would maybe write down these 6 steps. Then could be a question, prove the approximation ratio of 1.5, for which you might be report these 3 inequalities. But understanding beyond knowledge, I might ask you to explain, why does the first inequality hold? Why does the second inequality hold? Why does the third inequality hold? And this is where your explanation will become crucial, would become crucial. Okay, good. Yeah. That was Christofides algorithm. And we've used the trial inequality twice, because we've introduced shortcuts twice. First, by taking the green and red edges in the unknown optimal tour. And secondly, by skipping vertices when proceeding from Eulerian to a Hamiltonian cycle. And now we move on to another optimization problem, the knapsack problem. So what's the knapsack problem? Yeah, it's an optimization problem, but actually it comes in 2 variants, as a maximization problem and as a minimization problem. Yeah, some backstory. Imagine it's Christmas and you get a lot of presents, and then you want to take them home, but your knapsack can carry only so much. Ho, ho, ho. So the input to the problem is packets, and packets with certain values, non-negative integers, let's say, and they have weights. And your knapsack can carry only capital W weight, kilogram, let's say. And you want to put as much weight as possible, as much value as possible into your knapsack without having it break. So then it's a maximization problem. So you want to select a subset of all the packets, capital S, such that when you add up the values in that subset, it should be maximal, subject to the constraint that when adding the weights of the packets you've selected, it should be less or equal, that's a less or equal sign, than what your knapsack can carry, capital W. That's a maximization variant. The decision variant says, again, given the packets and given a value bound, you want to carry home at least that value, capital V. And weight bound, capital W. Is it even possible to satisfy both requirements? At least that value and at most that weight. That's a decision variant. And the minimization variant, we're given a value bound. We want to take home, by all means, Bigman 1, but we want to carry as little as possible. So we select the precious gifts of least weight first. So here we have the value bound, at least that value, and we want to minimize the weight. So, in conclusion, knapsack, 3 variants. As a maximization problem, maximize the value subject to the weight constraint, at most that weight. Minimization variant, value constraint, we want to have at least that value, minimize the weight. And the decision variant, is it possible to satisfy both constraints for given parameters capital V and capital W? And the decision variant is known to be NP complete, so we cannot even expect to solve either the maximization or the minimization variant exactly in polynomial time. And before proceeding to approximation algorithm for the knapsack, let's first try to devise a as efficient as possible an exact algorithm, even if it means exponential time. And we do that using dynamic programming. Maybe remember dynamic programming paradigm from CS300. Basically, you set up a table. It can be one-dimensional table, two-dimensional, or even higher dimensional table, such that the boundaries of that table are easy and such that calculating a new entry in that table is also easy. And then you gradually fill the table until hopefully at the end you arrive at the information you really want. That's what we do here. So today, to wrap things up, we discussed motivation and notion, the approximation factor for minimization and maximization problem. We discussed the traveling salesperson problem, decision problem, and minimization problem. We discussed the double tree algorithm and Christofides algorithm. Both make the first step the same, calculate a minimum spanning tree. And we've analyzed the double tree algorithm, seeing that it attains approximation ratio 2, at most twice as large a tour as the unknown optimal tour. whereas Christofides algorithm performs some more calculations, but it yields an approximation ratio 1.5 better. And this is almost the best that is still known nowadays. And then we started talking about the knapsack problem, 3 variants, maximization variant, maximize the value, minimization variant, minimize the weight, decision variant, and we've discussed a dynamic programming approach to solve that exactly, but this is running time of this algorithm is polynomial in capital V, which is the unknown output value, which is not polynomial in the binary input length. So thank you so much for your attention and see you again on Thursday.